Good morning, good evening, good afternoon. We are recording again a series on modeling and simulations of earthquakes, soil structures, and their interaction. Today's lecture is going to be on probabilistic modeling, in particular on so-called Karhunen-Loève expansion that's used in conjunction with polynomial chaos to characterize the statistics of the random field and random process, random field for the material, random process for the earthquake. And with me are Mr. Hershon Wang, who's going to talk about it. That's what he's been playing with for the last few years. And then Dr. Han Yang, who gave a few lectures ago and who's going to give a few more in the near future. My name is Boris Jeremic. We are at different sides of the world. I'm in Europe, in Zurich, in Switzerland. Hershon and Han are in Davis, in California, 9-hour zones on the other side. It's 6:15 p.m. in my zone. It's 9:15 a.m. in their zone, and it's Tuesday, May 12th. So welcome, and Hershon, go ahead, please.
Okay, yeah, I will
You
share
can
my
share
screen.
Your screen. Yes, yes.
Okay. And I will change this to.
Yes, change to one slide. Yes.
Yeah.
Okay.
Yeah. Yeah. Okay. Yeah. 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 Good morning. So today we will continue to talk about the uncertainty quantifications using Hermite polynomial KLs, and we will have a brief review of what we have mentioned yesterday. And so now we have uncertain equations of motions. As I mentioned, we're going to have some uncertainties in this system of equations. We will have some uncertain stiffness term on the right-hand side, and on the other side,
left-hand side, left-hand side, left-hand side.
On the left-hand side, yeah. On the other side, on the other hand, we will have a uncertain random forcing side, a random forcing for the right-hand side, and we need to solve this uncertain system equations, and this becomes the uncertain quantification problem. As I mentioned that we have two tasks need to perform. Number one is the uncertainty characterization. Essentially, we need to characterize what is the input uncertainty. For example, what's the input marginal distribution and input correlation structure of this stiffness term and of this random forcing term. And the second task is we need to do the uncertainty propagation. Essentially, we need to propagate this uncertain motion into our uncertain system to identify what is the probabilistic dynamic response of the system. You know, the mean, the standard deviation, or the PDF, or the correlation structure of your probabilistic displacement, velocity, and acceleration response. And we will first talk about this uncertainty characterization. And we need to basically characterize both the uncertain material parameters and also the uncertain ground motion. And the uncertain material parameters, can be characterized as the random field in the spatial domain. And the uncertain ground motions, they can be characterized as the random process in the time domain. As I mentioned that we can capture both of this uncertain material and uncertain ground motion, with the same, yes.
No, go ahead with the same process. But what I'm trying to say is that for the uncertain material, the E is not the elasticity; it's the elastic stiffness, which inside has elastic plastic stiffness. In fact, which inside has elasticity and plasticity, yield function and plastic flow directions, plastic flow, and everything else. So this E, you can think of it as a stiffness matrix, elastic plastic stiffness matrix. That is random and it's spatially variable. Yes.
Yes, that's true. Yeah, but we found out that both of these uncertain material parameters and these uncertain ground motions, actually they can mathematically can be represented by this generalized random field, where you have a generalized coordinate system that can either in spatial domain or either in temporal domain, and we need to quantify both of this arbitrary marginal distribution and arbitrary correlation structure of this such a generalized random field. And in last lecture, we already applied the polynomial chaos expansion to quantify the arbitrary marginal distribution. So today we're going to continue with the Karhunen-Loève expansion to capture the arbitrary correlation structure that may have for this generalized random field. And so this is the expansion of the Hermite polynomial chaos to the generalized random field. And here we have a underlying zero mean unit variance Gaussian random field. And we will call this as the kernel Gaussian random field. And we will construct our Hermite polynomial chaos based on this kernel Gaussian random field. The Hermite polynomial chaos will take the form like this, and it has the property of the zero mean and the mutual orthogonal. And we need to combine this Hermite polynomial chaos basis with the deterministic polynomial chaos coefficient field. And you need to choose some order of the polynomial chaos. We have done some experiment in the previous lecture. Now, if you have a very non-Gaussian and a marginal distribution has a relatively large variance, you might need a higher order P of polynomial chaos. But how about the correlation structure of this random field? We still not talk about the correlation of this random field. Well, the correlation structure need to be captured, need to be captured by this underlying Gaussian random field, and we will use a tool called Karhunen-Loève expansion to do that. So the first step to do that is we're going to uh, do a correlation structure mapping. So say this is the input correlation structure of your original generalized random field. We need to do the correlation structure mapping to map this correlation to the underlying correlation of the kernel Gaussian random field. As you can see here, they are connected by the deterministic Hermite polynomial chaos coefficient field. And once we solve this equation, we can identify the correlation structure of the underlying Gaussian random field. And then we can do a Karhunen-Loève expansion for such a kernel Gaussian random field. And essentially, it is an eigen decomposition, which says that the underlying Gaussian random field can be represented by this KL expansion, where this lambda I and Fix is the deterministic eigenvalue and eigenfunction of this kernel Gaussian correlation structure. And that this eigenvalue and eigenfunction that will meet this Fredholm's integral equation of the second type. And here, the uncertainty part goes to this Cassini I. So these are the two uncertainty, the different bases of the uncertainties of the standard Gaussian random variable. They are mutually independent and up to certain dimension of the certain dimension M that you need to choose in your Karhunen-Loève expansion. And we will show an example of this KL expansion. So to simplify our problem, we will consider the Gaussian random field so that you don't need to bother with the marginal distribution. We will fully focus on to capture the correlation structure. Suppose we have a yes.
Yeah. So you're assuming Gaussian field, but for
Uh-huh.
each of those, let's say you do PC expansion, each of those Gaussian fields is going to have its own
Yeah.
expansion in
Yeah, that's true.
Karhunen-Loève. Yeah. Okay. Okay.
Yeah, that's true. Yeah. So suppose we have a exponential correlation structure here, and our random field is distributed in 0 to 90 meters, and suppose we have a correlation length of 15 meters, and this correlation length is usually identified by the input. You need to input by the user. This can comes from the for example, the geotechnical characterization of your site. You can do multiple measurement, and you do a statistical analysis. You can identify such a correlation length. And in order to perform the KL expansion, we need to discretize our random field. So here we will initially discretize our random field at 4 different nodes. Essentially now we discretize this random field at into 4 different random variables at 4 different locations. And by the formula of the correlation, the exponential correlation, we can get this correlation structure, the correlation matrix of this random field. And then we can perform the eigen decomposition of such a correlation matrix. And we can get the eigenvalue and the eigenvector. Then we can combine this eigenvalue and eigenvector with some chosen dimension M. Then we can get this KL expansion. And here I'm showing you the different eigenmodes of this exponential correlation structure. And on the right-hand side, I'm showing you the synthesized correlation structure from a Karhunen-Loève expansion with different number of the dimensions. As you can see here, the thick black line discretized exact correlation structure of the original input, which is the exponential correlation. And you know, if we have only single dimension, you know, dimension 1, that means that the only source of the uncertainty is the single Gaussian random variable in our system. So all these 4 random variables, they just be represented by this single source of the uncertainty. So as you can see here, they are fully correlated, which means their correlation coefficient is 1. And if we increase the dimension of the uh, Karhunen-Loève expansion, you can see we can getting better to capture the correlation structure. And in this case, since we only have the 4 random variables, we only have 4 nodes in this in our discretization, and so with the KL dimension number 4, we can already fully capture the correlation structure of our discretized the correlation. But you might think that this is still not a very accurate representation of your original correlation structure. So we can increase we can increase the accuracy of our discretization. You know, we can increase the number of the elements in the model. We can reduce the mesh size into 3 meters. So now we have 30 elements to quantify such a 90 meters long the random field. And you can see here, now we have a much smooth, you know, discretized exact correlation structure. And originally dimension 4 can fully capture that not very accurate discretized correlation structure. But now if you use dimension 4, you will still have some errors in terms compared with the more accurate representation of the correlation. And in this case, you might need to increase your dimension to 30 to fully capture this smooth, more accurate correlation structure.
But
And
if I may add, so but I mean, so one has to decide at some point. I mean, first of all, how
yeah,
much data you have from the site, and
yeah,
then try to do the best with the amount of data. I don't think I've never heard
yeah,
that anybody goes with every 3 meters for testing something. You know, every 10,
yeah, yeah,
30
yeah.
meters maybe. So, but this is an excellent point that you have to go back and make sure that your dimension,
Mm-hmm.
that you have enough elements, that you have enough discretization to be able to model data that you actually have, because you're expanding the original data into these
Yeah.
expansion, and so you need to be able to verify that your expansion does a proper job for data that you have. That's good. Yeah.
Yeah, that's true. Yeah, and also even in this case, you have a very refined discretization. I don't think you really need to go to 30 dimension. For example, you can go to dimension number 10, which is
Yeah.
already quite a reasonable
Yes.
accuracy, right?
Yes.
Yeah. And also here, so we are showing the influence of the different correlation lengths.
Uh-huh.
So to identify the correlation structure, the correlation length is a very important parameter that control the decaying of the correlation. So our original correlation length is 50 meters. So now I'm showing you the 2 examples of the 20 meters and the 200 meters. So as you can see, the exact discretized correlation. So if we have a very short correlation length, your correlation going to decay very fast. That means that if we have one measurement at location 0, you basically cannot make any inference at say location at 80 meters, because they are almost not correlated at all. Yeah, that means your random field is very independent in terms of different locations. While on the other hand, if you have a very long correlation length, you can see you will have a relative slow decay of the correlation. That means that, yes.
Well, so finish, and then I'll jump in. I'm sorry.
Oh,
Yeah.
okay. Yeah, that means that if you have a measurement at say location 0, then you can have a very kind of a good confidence about what is going on at location 60 or 80 meters, even if they are kind of far away. Yeah.
So essentially, what you're saying is that the low correlation length means that the site is very variable.
Yes, very variable.
In this case, 20 meters, 30, 40, 50, 60 meters, it's a totally different material. And
Yeah.
you cannot make any inference about what's on that side if you know what's here, 20 meters away, or in
Yeah.
this case, 60 meters
Yeah.
away. On the other hand, if you have a very long correlation length, it's a very uniform material. So what is here is very similar to what is there, to what is there, to what is there. So of
Yeah.
course, in that case, you know, we can see here that you need many fewer dimensions, so the
Yeah.
problem becomes simpler. But you don't control that. It's the nature, you know, of the material. If the material is very uncertain, you need more
Yeah.
more dimensions. If material is very uniform, you need less dimensions. So stuff like.
Yeah, that's true. Yeah. So as professor mentioned that if you have a very, low correlation length and a very heterogeneous random field, dimension number 4 might not be enough. While for this case, if you have a very long correlation, that means your random field is more homogeneous.
Yeah.
Dimension 4 is already good accurate representation for the random field.
Yeah.
Yeah. And then we need to, after we perform the Karhunen-Loève expansion to capture the correlation structure, we need to combine this with the Hermite polynomial expansion for the marginal distribution. So eventually we can get this combined Hermite polynomial chaos and the Karhunen-Loève expansion of the original random field. And here, the phi I becomes the multi-dimensional Hermite polynomial chaos. Now the underlying bases are the different Gaussian random variables comes from the KL expansion. Now, you need to identify the order of the polynomial chaos and also the dimension of the KL expansion in order to do this KL PC and the KL expansion. And here, the DIX is the deterministic polynomial chaos coefficient field. As you can see here, the formula of the DIX is related to both the DP, which is coming from your marginal Hermite polynomial chaos expansion, and also the lambda I Fi, which comes from your KL expansion. So it contains both the information of the marginal distribution and also the correlation structure. One of the very important note here is that you need to properly choose the number of the order of the polynomial chaos and the dimension of the KL expansion. So generally speaking, so if you have a more non-Gaussian marginal distribution, or you have a relative large variance of your marginal distribution, you need to choose a larger number of the Hermite PC order. And if you have a more heterogeneous or have a very short correlation length of your random field in correlation structure, you need to choose a larger number of the dimension when you perform the KL expansion. And here I'm showing you.
I'm sorry. So
Yeah.
just go back one slide. So
Uh,
essentially, this is an excellent. But it's always a good idea to once you choose your order
yeah.
P and your order M, it's always a good
Uh,
idea to go back and check against the data and see how good is it, and can you
yeah.
reproduce the distributions, and can you reproduce the actual field,
Yeah. That's true. Yeah.
just like
That's true.
what you
Yeah.
showed before. Yes.
Yeah. That's true. Yeah. So here I'm showing the give you a direct expanded representation of the multidimensional Hermite polynomial chaos of dimension 3 and of order 3 and dimension number 4. So you can see for the zeros order we only have a constant term, and for the PC order 1 we have the standard Gaussian random variables of 4 dimension, and for the PC order 2 you will have a combination of either two of them or the second order of the single dimension, right? Like this one and this one. And so here I present a formula to calculate the total number of the Hermite polynomial chaos bases with a given dimension and a given order. As you can see here, we have a factorial here, which means that the number and the number of the Hermite polynomial chaos can go very fast if you increase the dimension or the order. So here is the table to show how fast they can grow. And if I have a PC order 2, if I increase the dimension from 5 to 15, your total number of PC can increase from 21 to 1300. So, but in practice, we wouldn't need to use a full complete Hermite polynomial chaos basis. We generally do some truncation. For example, if I choose a PC order 2 and the dimension 15, I don't need to go using the full 1300. This total number of PC. We might just choose first 300 or first 200 of the polynomial chaos. But as Professor Jeremic already mentioned, that it's very important if you do the truncation, you need to make sure you check the statistics synthesized from your Karhunen-Loève Hermite PC KL expansion to make sure you still can very accurately represent the data, the statistics in the data. And how to do that?
If I may go back, if I may add, so what this really means is, let's say you have a PC order 5
Uh-huh.
and you have
Uh-huh.
KL dimension 5 that goes to 252. That means that your
Yeah.
system grows 252 times.
Yeah, that's true.
So
Yeah.
if you had, for example, let's say a small finite element system with stochastic finite elements, stochastic elastic finite elements that has 1,000 degrees of freedom. If you do
Yeah.
this expansion of the random field, input random field into Karhunen-Loève of the dimension M5, and if you do the expansion into probabilistic space polynomial chaos 5, you're actually going to end with 252,000 degrees of freedom. Probabilistic degrees of freedom, but that's 252,000 for original 1,000 degrees of freedom, 1,000 nodes,
Yeah.
let's say if it's a 1D, or some shear wave or something like that. So these numbers
Yeah,
can
that's
grow
true.
quite fast, but as Heshan said, you can do some trimming, but the problem
Yeah.
becomes big. But what you are not doing, you're not doing Monte Carlo. This is much more accurate and much more efficient, and you get results in single shot, as opposed to Monte Carlo, where you have to do many thousands or millions of runs and so on. I'm sorry, go ahead.
Yeah. 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 And in order to check our Hermite polynomial chaos Karhunen-Loève expansion, we need to do the we need to know the statistics that can synthesize from this Hermite polynomial and Karhunen-Loève expansion, and we can calculate the marginal mean, which is essentially the first term of the deterministic uh, coefficient field, and also we can determine the variance synthesized from the expansion and also the correlation structure. And now you can also identify the PDF of such a random field by sampling this underlying Gaussian random field, essentially the different dimensions of the Gaussian random variable, and you can quickly generate the samples of the random field, and you can do a kernel density estimation to get the PDF, and you can check this PDF with your data, and then you can determine whether you need to increase the order or need to increase the dimension of the correlation. And with that, yeah,
Good, thank
I
you very
think
much.
that's all what I want to talk. Yeah.
So we now explained essentially the way to approach this problem, to expand into probability spaces using polynomial chaos, and to take
Yeah.
into the account the uncertain field, the random field of the material, all the coefficients, and also to take into account the uncertain process, the earthquake in this case, as
Yeah.
loads. We use
Yeah.
domain reduction method, so that's how we convert earthquake motions into loads. So
Yeah.
I guess next step will be to start talking about stochastic, elastic, plastic finite elements, but that's going to come next. Thank you
Yeah.
very much. We
Yeah.
will continue next time. Thank you.
Thank you.